Last section, we learned how to solve a special class of first-order differential equations, linear ones. In this section, we will study how to solve another class of first-order differential equations called separable differential equations. We define a separable first-order differential equation as one that can be written in the form n of y times dy dx is equal to m of x. I want to note that some resources will write the definition in different forms, such as m of x plus n of y times dy dx equals 0, which is just our form with m of x subtracted to the other side, off by a sign, or dy dx equals m of x times n of y, which we can get from our form by dividing by n of y on both sides, and rewriting 1 over n of y as just some other function of y, again called n of y. Or finally, m of x dx plus n of y dy equals 0, which is like the m of x plus n of y dy dx equals 0, but abusing the notation of dy dx and multiplying through by dx in the equation. All of these forms are equivalent up to a negative sign or an inverse or multiplication by dx. So while you may see any of these forms for a separable differential equation, we'll stick to the one introduced first while we build our theory. So using this form n of y times dy dx equals m of x, we want to be able to solve for y. To do this, we can integrate both sides with respect to x. And this gives us the integral of n of y times dy dx dx on the left and the integral of m of x dx on the right. And the left-hand side can be simplified using the substitution rule again. The integral of n of y times dy dx dx is equal to the integral of n of y dy. And notice each of these integrals, the integral of n of y dy and the integral of m of x dx, are the types of integrals we learned how to solve in Calc 2. So solving each of these, we can get a relationship between y and x to find our solution. Let's look at an example. In this example, we want to find solutions to the differential equation dy dx equals x squared over 1 minus y squared. We can see that this is a nonlinear differential equation because of the y squared in the denominator on the right. To see that it's separable, we'll want to multiply both sides by 1 minus y squared to get 1 minus y squared times dy dx is equal to x squared. Now we have a function of y, 1 minus y squared, times dy dx is equal to a function of x, x squared. So we can integrate both sides with respect to x, as we said above, to have the integral of 1 minus y squared dy is equal to the integral of x squared dx. On the right, we get x cubed over 3 plus some constant c, and on the left, we get y minus y cubed over 3. We could put in another constant of integration, but we'll just clump them together in that 1 plus c. So we can conclude that the solutions of y satisfy the equation y minus y cubed over 3 is equal to x cubed over 3 plus c. So while we found this equation giving a relationship between x and y, I want to note that we can't solve this explicitly for y by itself. So we call this an implicit solution to the differential equation, because y is implicitly defined in terms of x, rather than explicitly where we have an equation like y equals some function of x. Oftentimes, nonlinear differential equations, like most separable differential equations are, cannot be solved explicitly. However, implicit solutions are often just as useful in applications because we can still compute numerical answers in terms of x and y and create integral curves or the graphs of solutions from them. So while it's preferable to get an explicit solution, implicit solutions are very valuable as well.